Picture this, a world where the skies burn with a toxic yellow haze, where the surface is hot enough to melt lead, and where the air feels like a crushing weight pressing down on you. This isn't a scene from a science fiction movie. This is Venus, Earth's so-called evil twin. At first glance, Venus seems like a close cousin to our own planet, with a similar size and composition. But beneath its deceptively familiar appearance lies a world of chaos and mystery, one that defies everything we think we know about planets. From its runaway greenhouse effect to its bizarre atmospheric phenomena, Venus is a puzzle that scientists are still struggling to solve. And today, we're diving into 25 of its most baffling mysteries, secrets that could rewrite our understanding of the solar system. So, buckle up, because what you're about to discover will leave you questioning everything you thought you knew about the universe. Now turning to the first of Venus's many mysteries, we encounter the runaway greenhouse effect, a phenomenon that has transformed the planet into a blistering inferno. Unlike Earth, where the greenhouse effect helps maintain a stable and habitable climate, Venus's version has spiraled out of control. Temperatures on its surface soar to a staggering 864 degrees Fahrenheit, hot enough to melt lead. But what makes Venus's greenhouse effect so extreme? On Earth, greenhouse gases like carbon dioxide trap just enough heat to keep our planet warm. Venus, however, is shrouded in a thick atmosphere composed almost entirely of carbon dioxide, with clouds of sulfuric acid adding to the mix. This dense atmosphere traps heat relentlessly, creating a feedback loop where temperatures rise uncontrollably. Scientists are baffled by how this process became so intense. Some theories suggest that Venus may have once had oceans, which evaporated as the planet warmed, releasing even more greenhouse gases into the atmosphere. Others propose that volcanic activity billions of years ago released massive amounts of carbon dioxide, kickstarting the runaway effect. What makes this mystery even more intriguing is its relevance to Earth. Venus serves as a cautionary tale, showing us what could happen if greenhouse gases accumulate unchecked. By studying Venus, scientists hope to better understand the delicate balance that keeps Earth's climate stable and what might push it over the edge. This runaway greenhouse effect isn't just a curiosity, it's a window into the past, present, and future of planetary climates. And as we continue to explore Venus, we may uncover clues that could help us protect our own planet from a similar fate. Now shifting our gaze to another enigma of Venus, we delve into the mystery of its missing water. Evidence suggests that Venus may have once been a very different world, possibly even home to vast oceans. But today, the planet is a dry, desolate wasteland. So, where did all the water go? Scientists believe that billions of years ago, Venus could have had enough water to cover its surface, much like Earth. However, something catastrophic happened. One leading theory points to the planet's proximity to the Sun. As Venus warmed, its oceans began to evaporate, releasing water vapor into the atmosphere. Without a protective magnetic field, Venus was vulnerable to the Sun's powerful solar winds. These winds, composed of charged particles, stripped away the hydrogen atoms from the water molecules, breaking them apart and sending them into space. Over time, this process left Venus with almost no water at all. Another factor contributing to the disappearance of water is Venus's intense chemical reactions. The planet's thick atmosphere, rich in carbon dioxide, interacts with water vapor to form carbonic acid. This acid then breaks down further, releasing hydrogen into space and leaving behind oxygen, which reacts with the surface rocks. These chemical processes, combined with the relentless solar winds, created a perfect storm that drained Venus of its water. What makes this mystery so fascinating is its implications for understanding planetary evolution. Venus serves as a stark reminder of how delicate the balance of water and atmosphere can be. By studying what happened to Venus, scientists hope to gain insights into the conditions that allow a planet to retain its water or lose it forever. This missing water isn't just a puzzle for Venus, it's a key to understanding the potential fates of other worlds, including our own. As we continue to explore Venus, we may uncover more clues about how water shapes the destiny of planets across the cosmos. Now turning to one of the most baffling phenomena in our solar system, we encounter the super-rotation of Venus's atmosphere. Unlike any other planet, Venus's atmosphere spins around the planet at an astonishing speed, completing a full rotation in just 4 Earth days. This is incredibly fast, especially when you consider that Venus itself takes 243 Earth days to complete a single rotation on its axis. In other words, the atmosphere is whipping around the planet 60 times faster than the surface below. This bizarre behavior defies everything we know about atmospheric science, leaving scientists scratching their heads. So, what could possibly be driving this super-rotation? One leading theory points to thermal tides. On Venus, the sun heats the atmosphere unevenly, creating massive temperature differences between the day and night sides. This imbalance generates powerful winds that push the atmosphere forward, accelerating its rotation. Another factor could be momentum transfer. As the thick, dense atmosphere interacts with the planet's surface, energy is transferred from the ground to the air, further fueling the rapid spin. These forces combine to create a runaway effect, causing the atmosphere to race around the planet at breakneck speeds. But why doesn't this happen on Earth or other planets? The answer lies in Venus's unique conditions. Its thick atmosphere, composed mostly of carbon dioxide, acts like a giant blanket, trapping heat and creating extreme pressure. This dense environment allows the winds to build up incredible momentum, something that thinner atmospheres like Earth simply can't sustain. Additionally, Venus's slow rotation means there's less friction to slow down the atmosphere, allowing it to maintain its high-speed spin. The super-rotation of Venus's atmosphere isn't just a scientific curiosity. It has profound implications for understanding planetary atmospheres. By studying this phenomenon, scientists hope to uncover clues about how atmospheres evolve and interact with their planets. It also raises intriguing questions about the potential for similar processes on exoplanets, especially those with thick, Venus-like atmospheres. As we continue to explore Venus, this mystery serves as a reminder of how much we still have to learn about the complex dynamics of planetary systems. And with that, we move closer to unraveling the next enigma of this enigmatic world. Now shifting our gaze to another electrifying mystery, we delve into the strange and puzzling phenomenon of lightning on Venus. Unlike Earth, where lightning is commonly associated with thunderstorms and water clouds, Venus presents a unique challenge to our understanding. Here, lightning has been detected in a thick, dry atmosphere dominated by carbon dioxide, with no water clouds in sight. This raises the question, how does lightning form in such an alien environment? On Earth, lightning is generated when water droplets and ice particles collide within storm clouds, creating electrical charges that eventually discharge as bolts of lightning. But Venus, with its scorching surface temperatures and sulfuric acid clouds, lacks the water necessary for this process. So, what's causing the lightning? One theory suggests that the sulfuric acid clouds themselves could be the key. These clouds, composed of droplets of sulfuric acid, might generate electrical charges through chemical reactions or friction as they move through the dense atmosphere. Another possibility is that volcanic activity on Venus could be producing ash and particles that, when ejected into the atmosphere, create the conditions for lightning. The existence of lightning on Venus is not just a scientific curiosity. It has significant implications for understanding the planet's atmospheric chemistry. Lightning can break apart molecules in the atmosphere, triggering complex chemical reactions that might explain some of the unusual compounds detected in Venus's clouds. For example, the presence of phosphine gas, which has sparked debates about potential microbial life, could be linked to these electrical discharges. Additionally, studying Venusian lightning could provide insights into how lightning behaves in extreme environments, which could be relevant for understanding exoplanets with similar conditions. What makes this mystery even more intriguing is the way it challenges our assumptions about planetary atmospheres. Venus's lightning suggests that the processes driving electrical activity might be far more diverse than we once thought. It also highlights the importance of exploring worlds that defy our expectations, as they often hold the keys to unlocking new scientific discoveries. As we continue to investigate this enigmatic phenomenon, we're reminded that Venus, despite its harsh and inhospitable nature, still has secrets waiting to be uncovered. And with that, we prepare to explore yet another layer of this mysterious world. Now turning to another captivating mystery, we explore the enigmatic dark streaks that have been observed in Venus's upper atmosphere. These streaks, which appear as shadowy patches against the planet's bright clouds, have puzzled scientists for decades. Unlike the lightning we just discussed, these dark features don't seem to be tied to electrical activity. Instead, they hint at something far more complex and potentially even more intriguing. One of the leading theories suggests that these streaks could be the result of volcanic activity. Venus is known to have a surface dotted with volcanoes, some of which may still be active. If volcanic eruptions are releasing ash or other particles into the atmosphere, these materials could be carried by winds, forming the dark streaks we see. This idea is supported by the fact that Venus's atmosphere is incredibly dynamic, with winds reaching speeds of hundreds of kilometers per hour. These powerful winds could easily transport volcanic debris across vast distances, creating the streaks that stretch across the planet's skies. Another possibility is that the streaks are caused by chemical reactions occurring within Venus's atmosphere. The planet's thick clouds are composed primarily of sulfuric acid, a highly reactive substance. Under certain conditions, chemical reactions could produce dark compounds that settle into streaks. For example, sulfur compounds might undergo changes when exposed to sunlight or other atmospheric conditions, leading to the formation of these mysterious features. This theory aligns with observations of Venus's atmosphere, which is known to be rich in sulfur-based molecules. Perhaps the most tantalizing theory is that these dark streaks could be evidence of microbial life. While it might sound like science fiction, some scientists have speculated that microorganisms could exist in Venus's upper atmosphere, where temperatures and pressures are more moderate compared to the planet's scorching surface. These microbes, if they exist, might produce dark pigments as a byproduct of their metabolism, creating the streaks we observe. This idea gained traction with the recent detection of phosphine gas in Venus's atmosphere, which some researchers believe could be a potential biosignature. However, this theory remains highly speculative and requires further investigation. Studying these dark streaks is no easy task. Venus's thick atmosphere and extreme surface conditions make it difficult for probes to gather detailed data. Most of what we know comes from observations made by spacecraft orbiting the planet or from telescopes on Earth. These limitations mean that many questions about the streaks remain unanswered. Are they truly volcanic in origin? Do they result from chemical processes? Or could they hint at something even more extraordinary, like life? Each possibility opens up new avenues for exploration and challenges our understanding of Venus's complex atmosphere. What makes these dark streaks so significant is their potential to reveal hidden aspects of Venus's environment. Whether they're formed by volcanoes, chemical reactions, or even microbial activity, they offer a window into the planet's atmospheric dynamics and geological history. As we continue to study these enigmatic features, we're reminded once again that Venus, despite its harsh and inhospitable nature, holds secrets that could reshape our understanding of planetary science. And with that, we prepare to uncover yet another layer of this mysterious world. Now shifting our focus to the ground beneath Venus's swirling clouds, we encounter another perplexing mystery, the lack of plate tectonics. Unlike Earth, where the surface is divided into moving plates that constantly reshape the planet, Venus appears to have a static crust. This absence of plate tectonics is one of the most striking differences between the two planets, and it raises a host of questions about Venus's geological history and its current state. Scientists have long wondered why Venus doesn't exhibit the same tectonic activity as Earth. One key piece of evidence comes from the planet's surface, which shows signs of past tectonic activity. For example, Venus has vast regions of fractured and folded terrain, suggesting that its crust was once mobile. These features hint that Venus may have experienced tectonic processes in its early history, but something caused them to stop. The question is, what one leading theory points to Venus's extreme surface conditions? The planet's scorching temperatures, which can reach up to 470 degrees Celsius, may have caused the crust to become too hot and soft to break into plates. On Earth, the cooler crust allows for rigid plates to form and move, but on Venus, the intense heat could have prevented this process. Additionally, Venus's lack of water might play a role. Water on Earth acts as a lubricant, helping plates slide past one another. Without it, Venus's crust may have become too rigid and immobile. Another possibility is that Venus's interior cooled differently than Earth's. Plate tectonics on Earth are driven by the movement of molten rock in the mantle, which generates the forces needed to push and pull the plates. If Venus's mantle cooled more quickly or became less dynamic, it could have stopped the tectonic processes altogether. This idea is supported by the fact that Venus has fewer volcanic hotspots than Earth, suggesting that its interior may be less active. The lack of plate tectonics has profound implications for Venus's surface and atmosphere. On Earth, plate tectonics play a crucial role in recycling carbon dioxide, a process that helps regulate the planet's climate. When plates collide, carbon-rich rocks are pushed into the mantle, where the carbon is eventually released through volcanic activity. This cycle keeps Earth's atmosphere in balance. On Venus, however, the absence of plate tectonics means that carbon dioxide isn't recycled in the same way. Instead, it accumulates in the atmosphere, contributing to the planet's runaway greenhouse effect and making it the hottest planet in the solar system. This mystery also affects how we interpret Venus's surface features. Without plate tectonics, the planet's crust doesn't experience the same kind of renewal and reshaping that Earth does. Instead, Venus's surface is dominated by volcanic plains, impact craters, and unique formations like the pancake domes we'll explore later. These features suggest that Venus's geology is shaped more by volcanic activity and internal heat than by the movement of plates. As we continue to study Venus, the question of why it lacks plate tectonics remains a central puzzle. Understanding this mystery could not only shed light on Venus's past, but also provide insights into how planetary systems evolve. It challenges us to rethink our assumptions about what makes a planet geologically active and reminds us that even our closest planetary neighbor holds secrets that defy easy explanation. And with that, we prepare to delve into another fascinating feature of this enigmatic world. Now turning to the fiery heart of Venus, we encounter a landscape dominated by one of the most striking features of the planet, its volcanoes. Venus is home to more volcanoes than any other planet in the solar system, with estimates ranging into the hundreds of thousands. Yet, despite their sheer number, these volcanoes present a puzzling mystery. Most of them appear to be dormant, raising questions about Venus's volcanic activity, both past and present. One of the biggest challenges in studying Venus's volcanoes is the planet's thick, toxic atmosphere. The dense clouds of sulfuric acid make it nearly impossible to observe the surface directly using traditional telescopes. Instead, scientists rely on radar data from missions like NASA's Magellan spacecraft, which mapped Venus's surface in the 1990s. These images revealed a world covered in volcanic plains, towering shield volcanoes, and strange formations like the pancake domes we'll explore later. But while the data shows evidence of past eruptions, confirming recent volcanic activity has proven far more difficult. Some scientists believe that Venus may still be volcanically active today. Clues come from the planet's atmosphere, which shows fluctuations in sulfur dioxide levels. On Earth, similar changes are often linked to volcanic eruptions. However, Venus's atmosphere is so dynamic and complex that these variations could also be caused by other processes, such as chemical reactions or atmospheric circulation. Without direct observations of an eruption, it's hard to say for sure. Another intriguing piece of evidence comes from the planet's surface. Some regions show features that resemble fresh lava flows, with smooth, uneroded surfaces that suggest they could be relatively young, perhaps only a few million years old or even less. While this is ancient by human standards, it's a blink of an eye in geological terms. If these flows are indeed recent, it would mean that Venus's volcanoes aren't entirely dormant. But again, the lack of direct evidence leaves room for debate. Theories about Venus's volcanic history are just as fascinating. Some researchers suggest that the planet may have experienced massive volcanic resurfacing events in its past. These cataclysmic eruptions would have covered vast areas of the surface in lava, effectively wiping out older geological features. This could explain why Venus's surface appears relatively young compared to other rocky planets like Mars or Mercury. However, the exact timing and cause of these events remain unclear. The implications of Venus's volcanic activity extend far beyond the planet itself. Understanding how and why volcanoes behave on Venus could shed light on the geological processes that shape rocky planets, including Earth. For example, Venus's lack of plate tectonics means that its volcanoes are likely driven by different mechanisms than those on Earth. Studying these differences could help us better understand the forces that drive volcanic activity across the solar system. As we continue to explore Venus, the mystery of its volcanoes remains a tantalizing puzzle. Are they truly dormant, or is there still fire beneath the surface? Future missions like NASA Veritas and the European Space Agency's Envision aim to answer these questions by mapping Venus's surface in unprecedented detail and searching for signs of active volcanism. Until then, the volcanoes of Venus stand as a reminder of the planet's dynamic and enigmatic nature, challenging us to uncover the secrets hidden beneath its thick, swirling clouds. And with that, we prepare to delve into another of Venus's geological wonders, now shifting our focus to one of Venus's most peculiar geological features. We encounter the enigmatic pancake domes. These strange, flat-topped formations dot the planet's surface, resembling stacks of pancakes scattered across a vast volcanic plain. But what exactly are these domes, and how did they come to be? Their unique shape and structure have puzzled scientists for decades, offering a fascinating glimpse into the complex geology of Venus. Pancake domes are typically circular, with steep sides and flat tops, ranging from a few kilometers to over 60 kilometers in diameter. Their distinctive appearance sets them apart from other volcanic features found in the solar system. Unlike the towering shield volcanoes of Earth or Mars, these domes are relatively low and wide, giving them their pancake-like profile. But what makes them even more intriguing is the mystery surrounding their formation. One leading theory suggests that pancake domes are the result of highly viscous lava flows. On Earth, lava with high viscosity tends to pile up in thick, slow-moving mounds, creating dome-like structures. However, the lava on Venus may have been even thicker, possibly due to its unique chemical composition or the planet's extreme surface pressure, which is about 90 times that of Earth. This thick lava would have oozed out slowly, spreading outward but not flowing far, resulting in the flat, wide shapes we see today. Another factor that may have contributed to the formation of pancake domes is Venus's thick atmosphere. The planet's dense air could have played a role in cooling the lava more quickly, preventing it from spreading too far and encouraging it to solidify into these distinct shapes. Some scientists also speculate that the domes might have formed when lava interacted with water or other volatile substances beneath the surface, causing explosive eruptions that left behind these peculiar structures. Despite these theories, the exact process behind the formation of pancake domes remains unclear. Their unique shape doesn't perfectly match any known volcanic features on Earth or other planets, making them a true geological mystery. Some researchers have even proposed that they could be the result of a combination of factors, such as multiple eruptions over time or the interaction of lava with Venus's unique surface conditions. The study of pancake domes isn't just about solving a geological puzzle, it also provides valuable insights into Venus's volcanic history and the forces that shape its surface. By understanding how these domes formed, scientists can learn more about the planet's internal heat, its volcanic activity, and even its potential for past or present habitability. Future missions to Venus, equipped with advanced imaging and radar technology, may finally shed light on these enigmatic features, helping us unravel the secrets of their origins. As we continue to explore the mysteries of Venus, the pancake domes stand as a testament to the planet's dynamic and complex geology. Their unusual shape and uncertain origins remind us that Venus is a world full of surprises, challenging our understanding of how volcanic processes work across the solar system. And with that, we prepare to delve into another of Venus's geological wonders, where new mysteries await. Now turning to another of Venus's geological enigmas, we encounter the mysterious tessary terrain. This unique landscape is unlike anything found on Earth or any other planet in the solar system. Characterized by its intricate, fractured patterns, the tessary terrain resembles a jigsaw puzzle of ridges, valleys, and plateaus, all interlocking in a complex mosaic. But what makes this terrain so special, and what secrets does it hold about Venus's past? The tessary terrain stands out because of its highly deformed surface, marked by multiple intersecting fractures and folds. These features suggest that this region has undergone intense geological activity, possibly involving both compression and extension forces. Unlike the smoother plains that dominate much of Venus's surface, the tessary terrain is rugged and chaotic, hinting at a turbulent history of tectonic upheaval. One of the leading theories about the formation of tessary terrain involves ancient crustal movements. Scientists believe that these regions may represent some of the oldest surfaces on Venus, preserved from a time when the planet's crust was more dynamic. The complex patterns could be the result of tectonic forces pushing and pulling the crust, creating a network of fractures and ridges. Some researchers even suggest that the tessary terrain might have formed during a period when Venus had a more Earth-like plate tectonic system, which later ceased to operate. Another intriguing possibility is that the tessary terrain was shaped by mantle plumes, upwellings of hot material from deep within Venus's interior. These plumes could have pushed against the planet's crust, causing it to buckle and fracture in intricate patterns. Over time, as the plumes subsided, the surface may have cooled and solidified, leaving behind the rugged terrain we see today. This theory aligns with observations of similar features on Earth, where mantle plumes have created uplifted and fractured regions. The study of tessary terrain is not just about understanding Venus's geological history, it also provides clues about the planet's internal dynamics. By analyzing the patterns and structures within these regions, scientists can infer how Venus's crust and mantle have interacted over billions of years. This information is crucial for piecing together the planet's evolution and understanding why it diverged so dramatically from Earth, despite their similar size and composition. As we continue to explore Venus, the tessary terrain remains a focal point for researchers seeking to unravel the planet's mysteries. Its complex patterns and ancient origins offer a window into a time when Venus may have been a very different world, with active tectonics and perhaps even conditions more conducive to life. Future missions equipped with advanced imaging and radar technology will undoubtedly shed more light on these enigmatic regions. bringing us closer to understanding the forces that shaped Venus into the planet we see today. With the tesserae terrain offering so many questions and possibilities, we now prepare to delve into another of Venus's geological wonders where new mysteries await. Now shifting our focus to another of Venus's puzzling features, we arrive at the absence of a global magnetic field. Unlike Earth, which is shielded by a strong magnetic field generated by its molten iron core, Venus lacks this protective barrier. This absence has profound implications for the planet, leaving its atmosphere and surface exposed to the full force of solar radiation. But why doesn't Venus have a magnetic field, and what does this mean for its habitability? One of the key reasons Venus lacks a magnetic field lies in the nature of its core. While Earth's core is molten and churns vigorously, creating the dynamo effect that generates our magnetic field, Venus's core appears to be either partially solid or not rotating fast enough to produce a similar effect. Scientists believe that Venus's slow rotation, taking 243 Earth days to complete one rotation, may play a significant role. Without the rapid spin needed to drive the dynamo, Venus's core remains relatively stagnant, unable to generate a magnetic field. The absence of a magnetic field has serious consequences for Venus. Without this protective shield, the planet's atmosphere is bombarded by solar winds, which strip away lighter molecules over time. This process may explain why Venus has lost much of its water and why its atmosphere is dominated by carbon dioxide, creating the runaway greenhouse effect we've discussed earlier. The lack of a magnetic field also means that Venus's surface is exposed to higher levels of radiation, making it an even more hostile environment for potential life. Another theory suggests that Venus's core might have cooled significantly over time, reducing its ability to generate a magnetic field. Unlike Earth, which has maintained a hot, active core, Venus may have experienced a different thermal evolution. Some researchers propose that Venus's core could have lost heat more rapidly due to its proximity to the Sun or differences in its internal structure. This cooling could have shut down the dynamo process, leaving the planet without a magnetic shield. The implications of this magnetic field absence extend beyond Venus itself. By studying why Venus lacks a magnetic field, scientists can gain insights into the conditions necessary for a planet to generate one. This knowledge is crucial for understanding the habitability of other planets, both within our solar system and beyond. If a planet's magnetic field is essential for protecting its atmosphere and surface from harmful radiation, then its presence or absence could be a key factor in determining whether a planet can support life. As we continue to explore Venus, the mystery of its missing magnetic field remains a central focus. Future missions, equipped with advanced instruments to study the planet's interior, may provide the answers we seek. Understanding why Venus lacks a magnetic field could not only solve one of its greatest mysteries, but also deepen our understanding of planetary evolution and the conditions necessary for habitability. With this enigma still unresolved, we now turn our attention to another of Venus's intriguing features, where new questions and discoveries await. Now turning to another of Venus's captivating mysteries, we encounter the strange phenomenon of what scientists have dubbed snow on its mountain peaks. This isn't the kind of snow we're familiar with on Earth, no icy flakes or frozen water here. Instead, Venus's snow is a highly reflective substance that coats the planet's highest elevations, creating a shimmering, almost metallic appearance. But what exactly is this mysterious material, and why does it only appear at these specific locations? One leading theory suggests that this snow could be composed of metallic compounds such as lead sulfide or bismuth sulfide. These materials have reflective properties and could condense at the cooler temperatures found on Venus's mountain peaks, which are significantly colder than the planet's scorching lowlands. On Venus, where surface temperatures average around 860 degrees Fahrenheit, the higher altitudes offer a slight reprieve. dropping to temperatures where certain metallic compounds might solidify and accumulate. Another possibility is that this reflective substance could be volcanic in origin. Venus is known for its extensive volcanic activity, and some scientists propose that the snow might be made up of minerals like pyrite, also known as fool's gold, which could be ejected during volcanic eruptions. These minerals might then settle on the cooler mountain peaks, creating the reflective coating we observe. However, this theory raises questions about how such materials could remain stable in Venus's harsh, acidic atmosphere, which is rich in sulfuric acid and other corrosive compounds. The existence of this snow is particularly puzzling because it challenges our understanding of Venus's surface conditions. The planet's atmosphere is incredibly dense, with pressures 92 times greater than Earth's, and its surface is dominated by extreme heat and corrosive chemicals. Yet, these reflective patches persist, defying expectations and hinting at processes we don't yet fully understand. What's more, the snow appears to be localized, only forming at high altitudes, which adds another layer of complexity to this mystery. This phenomenon also provides valuable insights into Venus's geology and atmospheric dynamics. The presence of such reflective materials suggests that Venus's surface chemistry is far more varied and dynamic than previously thought. It also highlights the stark contrasts between the planet's lowlands and highlands, where temperature and pressure differences create unique environments that could host unexpected geological processes. As we continue to study Venus, the mystery of its mountain, snow, remains a tantalizing puzzle. Future missions equipped with advanced imaging and spectroscopic tools may help us identify the exact composition of this reflective substance and uncover the mechanisms behind its formation. Understanding this phenomenon could not only solve one of Venus's many mysteries, but also deepen our knowledge of how planetary surfaces evolve under extreme conditions. With this intriguing mystery still unsolved, we now shift our focus to another of Venus's enigmatic features, where new discoveries and questions await. Now shifting our gaze to another of Venus's perplexing mysteries, we encounter the unexplained brightness variations that have puzzled scientists for decades. Unlike the steady glow of most planets, Venus exhibits fluctuations in its brightness that change over time, creating a dynamic and unpredictable appearance. These variations are not just subtle shifts, they are significant enough to be observed from Earth, raising questions about what could be causing such dramatic changes on a planet shrouded in thick clouds. One possible explanation for these brightness variations lies in Venus's atmosphere. The planet's dense, sulfuric acid-laden clouds are constantly in motion, driven by powerful winds and atmospheric currents. Changes in the thickness or composition of these clouds could alter how sunlight is reflected, leading to noticeable differences in brightness. For instance, if a layer of clouds becomes thicker or more reflective, Venus might appear brighter from our vantage point. Conversely, if the clouds thin out or absorb more light, the planet could dim. This atmospheric dance creates a complex interplay of light and shadow, making Venus's brightness a moving target for observers. Another intriguing possibility is that volcanic activity could be influencing these variations. Venus is home to some of the most extensive volcanic systems in the solar system, and while most of its volcanoes appear dormant, there is evidence to suggest that some may still be active. If a volcanic eruption were to occur, it could release gases and particles into the atmosphere, altering its reflective properties. These volcanic emissions might create temporary bright spots or dark patches, contributing to the overall fluctuations in brightness. However, confirming this theory is challenging, as Venus's thick atmosphere makes it difficult to directly observe surface activity. Surface changes could also play a role in these brightness variations. Venus's surface is a harsh, rocky landscape marked by vast plains, towering mountains, and mysterious geological features. If large-scale surface alterations, such as landslides or the formation of new lava flows, were to occur, they could change how sunlight interacts with the planet's surface. For example, freshly exposed rock or volcanic material might reflect light differently than older, weathered surfaces. These changes, though subtle, could contribute to the overall brightness variations observed over time. What makes these brightness variations so fascinating is that they challenge our understanding of Venus's atmosphere and surface dynamics. The planet's thick clouds and extreme surface conditions create an environment where even small changes can have significant effects. These fluctuations also highlight the interconnected nature of Venus's systems, how atmospheric processes, volcanic activity, and surface geology all influence one another in ways we are still striving to comprehend. As we continue to study Venus, these brightness variations remain a key area of interest. Future missions equipped with advanced imaging and spectroscopic tools may help us unravel the mechanisms behind these changes, shedding light on the complex interplay of forces at work on our neighboring planet. Understanding these variations could not only solve one of Venus's enduring mysteries, but also provide valuable insights into the behavior of planetary atmospheres and surfaces under extreme conditions. With this mystery still unfolding, we now turn our attention to another enigmatic feature of Venus, where new discoveries and questions await. Now turning to one of the most visually striking mysteries of Venus, we encounter the enigmatic double vortexes at the planet's poles. These swirling, hurricane-like formations are unlike anything seen on Earth or any other planet in our solar system. What makes them so peculiar is their dual structure, two distinct vortices spinning in opposite directions, creating a mesmerizing and chaotic dance in Venus's upper atmosphere. But how do these vortexes form, and what do they tell us about the planet's atmospheric behavior? The formation of these double vortexes is closely tied to Venus's super-rotating atmosphere, where winds race around the planet at speeds far exceeding its slow rotation. At the poles, these high-speed winds converge, creating a complex interplay of forces that give rise to the vortexes. The intense atmospheric pressure and the planet's unique thermal dynamics further shape these formations, resulting in their distinctive double structure. Unlike Earth's polar vortexes, which are relatively stable, Venus's double vortexes are highly dynamic, constantly shifting and changing shape. One leading theory suggests that the double vortexes are a result of the planet's extreme greenhouse effect. Venus's thick atmosphere traps heat, creating a uniform temperature across much of the planet. However, at the poles, the temperature gradient is steeper, causing air to sink and rise in a turbulent pattern. This instability, combined with the planet's rapid atmospheric circulation, could explain why the vortexes form in such a unique and unpredictable manner. The double structure may also be influenced by the interaction between the planet's surface and its atmosphere, though the exact mechanisms remain unclear. Another intriguing aspect of these vortexes is their behavior over time. Observations from missions like the European Space Agency's Venus Express have shown that the vortexes are not static. They can merge, split, or even disappear entirely before reforming. This erratic behavior challenges our understanding of atmospheric dynamics and raises questions about the forces driving these changes. Some scientists speculate that internal heat from Venus's core or even volcanic activity could play a role in shaping the vortexes, though direct evidence is scarce. What makes these double vortexes so significant is what they reveal about Venus's atmospheric circulation. They act as windows into the planet's complex weather systems, offering clues about how energy and momentum are distributed across its atmosphere. By studying these vortexes, scientists hope to gain a better understanding of not only Venus, but also the broader principles governing planetary atmospheres. This knowledge could even shed light on similar phenomena on exoplanets, expanding our understanding of atmospheric dynamics across the universe. As we continue to explore Venus, the double vortexes at its poles remain a captivating mystery. Future missions equipped with advanced imaging and atmospheric probes may provide the data needed to unravel their secrets, offering new insights into the forces that shape this enigmatic planet. With each discovery, we move closer to understanding the intricate dance of Venus's atmosphere and the mysteries that lie within. Now shifting our gaze to another captivating mystery, we encounter the enigmatic blue halo that has been observed around Venus during certain observations. This rare and ethereal phenomenon appears as a faint bluish glow surrounding the planet, creating an almost otherworldly aura. But what causes this mysterious halo, and what secrets does it hold about Venus's atmosphere? One of the leading explanations for the blue halo is atmospheric scattering. Venus's thick atmosphere, composed primarily of carbon dioxide with traces of sulfuric acid clouds, interacts with sunlight in unique ways. When sunlight passes through the planet's upper atmosphere, it can scatter in a manner similar to how Earth's atmosphere scatters light to create a blue sky. On Venus, this scattering effect might be amplified by the presence of tiny particles or aerosols in the atmosphere, creating the faint blue glow that observers have reported. Another possibility is that the blue halo is an optical illusion caused by the way light interacts with Venus's dense atmosphere and the viewing angle from Earth or spacecraft. For instance, when Venus is observed near the horizon or under specific lighting conditions, the bending and filtering of light through its atmosphere could produce the illusion of a blue halo. This phenomenon might also be influenced by the planet's reflective clouds, which could scatter light in unusual ways, adding to the halo's mystique. What makes the blue halo particularly intriguing is its rarity. Unlike other atmospheric phenomena on Venus, such as the double vortexes or superrotation, the blue halo has only been observed sporadically. This suggests that it may be the result of a specific combination of atmospheric conditions, making it a fleeting and unpredictable event. Scientists are still working to determine the exact circumstances under which the halo forms, as well as whether it is a consistent feature or a transient anomaly. The blue halo also offers valuable insights into the composition and behavior of Venus's atmosphere. By studying this phenomenon, researchers can learn more about the distribution and properties of aerosols and particles in the upper atmosphere. This information could help refine our understanding of how Venus's atmosphere interacts with sunlight and how it differs from Earth's. Additionally, the halo's rarity underscores the complexity of Venus's atmospheric dynamics, hinting at processes that we have yet to fully comprehend. As we continue to explore Venus, the blue halo remains a tantalizing mystery. Future missions equipped with advanced imaging technology and atmospheric sensors may provide the data needed to unravel its secrets. By shedding light on this elusive phenomenon, we can deepen our understanding of Venus's atmosphere and the forces that shape it, bringing us one step closer to solving the many mysteries of this enigmatic planet. Now shifting our focus to the surface of Venus, we encounter the puzzling phenomenon of unexplained hotspots. These areas, detected by various spacecraft and instruments, exhibit significantly higher temperatures compared to their surroundings, raising questions about what lies beneath the planet's scorching exterior. But what could be causing these mysterious hotspots, and what do they reveal about Venus's inner workings? One of the leading theories points to volcanic activity. Venus is known to have a vast number of volcanoes, some of which may still be active. These hotspots could be the result of molten lava flowing just beneath the surface or even erupting onto it. Unlike Earth, where volcanic activity is often accompanied by visible eruptions and ash clouds, Venus's thick atmosphere might mask these events, making it difficult to confirm. However, the heat signatures detected suggest that volcanic processes could be at play, releasing immense amounts of energy and creating these localized hot zones. Another possibility is that these hotspots are linked to tectonic forces. While Venus lacks the plate tectonics we see on Earth, it does have evidence of past tectonic activity, such as fractures and ridges. These features could indicate areas where the planet's crust is being stretched or compressed, generating heat through friction or the movement of magma beneath the surface. If this is the case, the hotspots might be windows into Venus's dynamic interior, offering clues about how the planet's crust and mantle interact. What makes these hotspots particularly intriguing is how they challenge our understanding of Venus's geology. On Earth, heat distribution is relatively well understood, with volcanic activity and tectonic movements following predictable patterns. Venus, however, presents a different story. The planet's surface appears to be dominated by vast plains and volcanic features, but the presence of these localized hotspots suggests that heat is not evenly distributed. This unevenness could indicate that Venus's interior is far more active and complex than previously thought, with pockets of intense heat driving geological processes in unexpected ways. The study of these hotspots also has broader implications for understanding planetary evolution. By analyzing their distribution and intensity, scientists can gain insights into how Venus manages its internal heat and why it differs so dramatically from Earth. This information could help us better understand the factors that shape rocky planets, including the role of heat in driving geological activity and atmospheric changes. As we continue to explore Venus, these hotspots remain a key area of interest. Future missions equipped with advanced thermal imaging and geological sensors may provide the data needed to unravel their origins. By shedding light on these mysterious features, we can deepen our understanding of Venus's geology and the forces that shape its surface, bringing us closer to solving the many mysteries of this enigmatic planet. Now turning to another intriguing mystery, we encounter the strange craters of Venus that defy expectations. Unlike the craters we see on the Moon or Mars, many of Venus's craters lack the typical features associated with impacts, such as raised rims, central peaks, or ejecta blankets. This raises a fascinating question. How did these craters form, and why do they look so different from those on other planets? One of the most compelling explanations lies in Venus's thick atmosphere. With a surface pressure over 90 times that of Earth's, Venus's atmosphere plays a significant role in shaping its surface features. When a meteoroid enters this dense atmosphere, it experiences intense friction and heat, often breaking apart or disintegrating before it can reach the surface. This means that only the largest or most resilient objects can create craters, and even then, the impact dynamics are drastically altered. The thick atmosphere acts like a cushion, softening the force of the impact and preventing the formation of the classic crater features we see elsewhere. Another theory suggests that Venus's surface itself may be responsible for the unusual appearance of these craters. The planet's surface is incredibly hot, with temperatures reaching nearly 900 degrees Fahrenheit, and it is covered in a layer of volcanic plains. Some scientists believe that the heat and the flow of lava over time could have reshaped or partially erased the original impact features, leaving behind craters that look smoother and less defined. This process, known as resurfacing, could explain why many of Venus's craters appear so different from those on other rocky worlds. What makes these craters even more puzzling is their distribution. On most planets, craters are scattered relatively evenly across the surface, but on Venus, they are clustered in certain areas while others remain almost entirely crater-free. This uneven distribution hints at a complex geological history, with some regions being resurfaced more recently than others. It also suggests that Venus's surface is far more dynamic than we once thought, with ongoing processes that continue to shape and reshape its landscape. The study of these strange craters not only deepens our understanding of Venus, but also provides valuable insights into how planetary surfaces evolve under different conditions. By comparing Venus's craters to those on other planets, scientists can better understand the role of atmospheres, surface temperatures, and geological activity in shaping impact features. This knowledge could even help us interpret the surfaces of exoplanets, offering clues about their atmospheres and histories. As we continue to explore Venus, these enigmatic craters remain a key area of interest. Future missions equipped with advanced imaging and geological tools may finally unravel the secrets behind their formation, shedding light on the forces that have shaped Venus's surface over billions of years. Each discovery brings us closer to understanding this mysterious planet and the unique processes that make it so different from the rest of the solar system. Now shifting our focus to another captivating mystery, we delve into the enigmatic coronae of Venus. These circular features scattered across the planet's surface are unlike anything found on Earth or other rocky worlds in our solar system. Coronae are thought to be the result of mantle plumes upwellings of hot material from deep within Venus's interior. But despite decades of study, their exact formation process remains a subject of intense debate among scientists. One of the leading theories suggests that coronae form when a mantle plume rises toward the surface, causing the crust above it to stretch and fracture. This creates a circular pattern of ridges and troughs, often surrounded by a ring of volcanic activity. Over time, the plume may cool and retreat, leaving behind a distinctive corona. However, not all coronae fit this model perfectly, leading researchers to question whether other forces, such as tectonic activity or even the planet's thick atmosphere, might play a role in their formation. What makes coronae particularly fascinating is what they reveal about Venus's interior. Unlike Earth, Venus lacks plate tectonics, which means its crust doesn't move in the same way. Instead, the planet's surface appears to be shaped by vertical forces like mantle plumes, pushing and pulling the crust from below. Coronae provide a window into these processes, offering clues about the temperature, composition, and dynamics of Venus's mantle. Some scientists even speculate that coronae could be evidence of ancient or ongoing volcanic activity, hinting at a more geologically active planet than previously thought. Another intriguing aspect of coronae is their connection to Venus's tectonic forces. While the planet doesn't have moving plates like Earth, it does exhibit signs of crustal deformation such as fractures and ridges. Some researchers believe that coronae could be the result of interactions between mantle plumes and these tectonic features, creating complex patterns that challenge our understanding of planetary geology. This interplay between volcanic and tectonic forces makes coronae a key area of study for unraveling Venus's geological history. The study of coronae also has broader implications for our understanding of other planets. By comparing Venus's coronae to similar features on Earth or even exoplanets, scientists can gain insights into how mantle plumes and tectonic forces shape planetary surfaces under different conditions. This knowledge could help us interpret the geology of distant worlds and better understand the diversity of planetary systems in the universe. As we continue to explore Venus, coronae remain a tantalizing mystery, offering a glimpse into the planet's hidden interior and the forces that have shaped its surface. Future missions, equipped with advanced imaging and geological tools, may finally uncover the secrets behind these enigmatic features, shedding light on the dynamic processes that make Venus such a unique and fascinating world. Each discovery brings us closer to understanding not only Venus but also the broader story of how planets evolve over time. Now turning to another intriguing feature of Venus, we encounter the mysterious arachnoids. These spider-like formations scattered across the planet's surface are unlike anything seen on Earth or other rocky worlds. Arachnoids are characterized by their radial patterns of fractures resembling the legs of a spider, often surrounding a central depression or dome. Their unique appearance has puzzled scientists for decades, sparking debates about their origins and what they might reveal about Venus's geological activity. One leading theory suggests that arachnoids are the result of volcanic processes. The central dome could be formed by magma pushing up from beneath the surface, creating a bulge that fractures the surrounding crust. As the magma cools and contracts, the fractures radiate outward, forming the distinctive spider-like pattern. This explanation ties arachnoids to Venus's volcanic history, hinting at a planet that may still be geologically active beneath its thick, hostile atmosphere. However, not all arachnoids fit neatly into this volcanic model. Some researchers propose that tectonic forces could also play a role in their formation. Venus's crust, though lacking plate tectonics, is still subject to stress and deformation. These forces might cause the crust to crack in radial patterns, creating arachnoids without the need for volcanic activity. This interplay between volcanic and tectonic processes adds another layer of complexity to understanding these enigmatic features. What makes arachnoids particularly fascinating is their uniqueness to Venus. No other planet in our solar system exhibits these spider-like formations, making them a key area of study for planetary scientists. Their presence suggests that Venus's geological processes are distinct from those of Earth or Mars, offering a glimpse into how different conditions, such as extreme heat and pressure, can shape a planet's surface in unexpected ways. Arachnoids also provide valuable clues about the planet's interior. The fractures and domes associated with these features indicate that Venus's crust is under constant stress, whether from volcanic activity, tectonic forces, or both. By studying arachnoids, scientists can gain insights into the planet's internal dynamics, including the movement of magma and the behavior of its crust under extreme conditions. The study of arachnoids has broader implications for our understanding of planetary geology. By comparing these features to similar formations on Earth or other planets, researchers can explore how different environments influence the formation and evolution of surface features. This knowledge could help us interpret the geology of exoplanets, expanding our understanding of the diverse ways planets can evolve. As we continue to explore Venus, arachnoids remain a captivating mystery, offering a window into the planet's complex geological processes. Future missions equipped with advanced imaging and geological tools may finally uncover the secrets behind these spider-like formations, shedding light on the forces that shape Venus's surface. Each discovery brings us closer to understanding not only Venus, but also the broader story of how planets evolve under extreme conditions. Now shifting our focus to another remarkable feature of Venus, we encounter the mysterious lava channels. These long, winding formations stretch across the planet's surface, with some extending for hundreds of kilometers, making them among the longest in the solar system. Unlike anything seen on Earth, these channels offer a fascinating glimpse into Venus's volcanic past and the unique conditions that shaped its surface. The formation of these lava channels is closely tied to Venus's volcanic activity. Scientists believe that vast amounts of molten rock or lava once flowed across the planet's surface, carving out these intricate pathways. The sheer length and complexity of the channels suggest that Venus experienced prolonged periods of volcanic eruptions, far more intense than those on Earth. This raises questions about the planet's internal heat and how it fueled such extensive volcanic activity. One of the most intriguing aspects of these lava channels is their relationship with Venus's thick atmosphere. The planet's dense carbon dioxide atmosphere creates extreme surface pressures and temperatures, which likely influenced how the lava flowed and cooled. Unlike Earth, where lava flows are often slowed by rapid cooling, Venus's atmosphere may have allowed lava to remain molten for longer periods, enabling it to travel greater distances and create these extensive channels. Another theory suggests that the composition of Venus's lava played a role in shaping these features. The lava on Venus is thought to be more fluid than Earth's, allowing it to flow more easily and form long, winding channels. This fluidity, combined with the planet's high temperatures and pressures, could explain why these channels are so much more extensive than those found on other rocky planets. The study of Venus's lava channels also provides insights into the planet's geological history. By analyzing their patterns and distribution, scientists can piece together the timeline of Venus's volcanic activity and understand how it has evolved over billions of years. These channels serve as a record of the planet's fiery past, offering clues about the forces that shaped its surface and interior. What makes these lava channels particularly significant is their potential to reveal more about Venus's habitability in the past. Some researchers speculate that the volcanic activity that created these channels may have released gases and water vapor into the atmosphere, potentially creating conditions suitable for life. While this remains a topic of debate, the lava channels are a key area of interest for future missions aiming to explore Venus's surface and atmosphere in greater detail. As we continue to unravel the mysteries of Venus, these lava channels stand as a testament to the planet's dynamic and fiery history. They remind us of the powerful forces at work in our solar system and the unique ways in which each planet evolves. Future missions, equipped with advanced imaging and geological tools, may finally uncover the secrets behind these extraordinary features, shedding light on the volcanic processes that shaped Venus and the broader story of planetary evolution. Now turning to another fascinating feature of Venus, we encounter the enigmatic wind streaks that crisscross its surface. These streaks, etched into the planet's landscape by powerful atmospheric winds, are a striking reminder of the dynamic forces at work in Venus's dense atmosphere. Unlike the smooth, uniform patterns we might expect, these streaks are incredibly complex, with intricate designs that have puzzled scientists for decades. The wind streaks on Venus are believed to form as high-speed winds sweep across the planet's surface, picking up fine particles of dust and volcanic ash and depositing them in long, flowing patterns. What makes these streaks so intriguing is their sheer variety. Some appear as thin, delicate lines, while others form broad, sweeping arcs. This diversity suggests that Venus's winds are not uniform but vary significantly in speed and direction, creating a tapestry of patterns that reflect the planet's turbulent atmospheric conditions. One of the key mysteries surrounding these wind streaks is their longevity. On Earth, wind-driven features like sand dunes are constantly shifting and changing due to weather and erosion. But on Venus, the wind streaks seem to persist for much longer periods, possibly due to the planet's thick atmosphere and lack of liquid water. This raises questions about how these features form and evolve over time. Are they the result of short, intense wind events, or do they slowly accumulate over centuries? Scientists are still working to unravel this puzzle. Another intriguing aspect of these streaks is their connection to Venus's surface composition. The particles that form the streaks are thought to come from volcanic eruptions, which have played a significant role in shaping the planet's surface. As these particles are carried by the wind, they interact with Venus's unique atmospheric chemistry, potentially altering their properties and contributing to the streaks' complex patterns. This interplay between surface and atmosphere offers valuable insights into Venus's geological and atmospheric processes. The study of wind streaks also provides clues about Venus's weather systems. The planet's atmosphere rotates much faster than its surface, a phenomenon known as superrotation. This creates powerful winds that can reach speeds of hundreds of kilometers per hour, far exceeding anything experienced on Earth. By analyzing the patterns of wind streaks, scientists can better understand how these winds behave and how they influence the planet's surface over time. What makes these wind streaks particularly significant is their potential to reveal more about Venus's climate history. By studying their distribution and orientation, researchers can piece together how the planet's atmospheric dynamics have changed over billions of years. This information could shed light on Venus's transformation from a potentially habitable world to the scorching, inhospitable planet we see today. As we continue to explore Venus, these wind streaks stand as a testament to the planet's ever-changing nature. They remind us of the powerful forces that shape planetary surfaces and the intricate connections between atmosphere and geology. future missions equipped with advanced imaging and atmospheric sensors may finally unlock the secrets behind these mysterious features, offering new insights into Venus's past and its place in the solar system. Now shifting our focus to another intriguing feature of Venus, we encounter the strange ridges and troughs that mark its surface. These formations, stretching across vast regions of the planet, are unlike anything seen on Earth, presenting a unique puzzle for scientists trying to understand Venus's geological history. The ridges often appearing as long, raised lines, and the troughs, which resemble deep, narrow valleys, create a complex network that hints at powerful forces shaping the planet's crust. One of the leading theories about the origins of these ridges and troughs involves tectonic activity. On Earth, tectonic plates move and collide, creating mountains, valleys, and other geological features. However, Venus lacks the same kind of plate tectonics, making the presence of these formations even more mysterious. Some scientists suggest that Venus may have experienced a different form of tectonic activity in the past, where the planet's crust stretched and fractured under immense pressure, forming these ridges and troughs. This idea challenges our understanding of how planetary surfaces evolve, as it implies that Venus's geological processes were once far more dynamic than they are today. Another possibility is that volcanic activity played a significant role in creating these features. Venus is home to numerous volcanoes, and some of the ridges and troughs could be the result of lava flows or the collapse of volcanic structures. For example, when lava cools and contracts, it can create cracks and fractures in the surface, leading to the formation of troughs. Similarly, the buildup of volcanic material over time might have formed ridges. This connection to volcanism highlights the interplay between Venus's surface and its internal heat, offering clues about the planet's geological activity over billions of years. What makes these ridges and troughs particularly fascinating is their scale and complexity. Some of these features stretch for hundreds of kilometers, forming intricate patterns that suggest multiple forces at work. The ridges, for instance, often appear in parallel lines, while the troughs can intersect and branch out in unexpected ways. This complexity raises questions about the timing and sequence of events that shaped Venus's surface. Were these features formed simultaneously, or did they develop over long periods through different geological processes? Scientists are still working to piece together this puzzle. The study of these ridges and troughs also provides valuable insights into Venus's internal structure. By analyzing their size, shape, and distribution, researchers can infer details about the planet's crust and mantle. For example, the presence of large, deep troughs might indicate areas where the crust is thinner or where internal heat has caused the surface to sink. Similarly, the ridges could point to regions where the crust has been compressed or uplifted. These clues help scientists build a more complete picture of Venus's geological history and its similarities and differences compared to Earth. As we continue to explore Venus, these enigmatic ridges and troughs serve as a reminder of the planet's dynamic past. They challenge our assumptions about planetary geology and highlight the need for further investigation. Future missions equipped with advanced imaging and radar technology may finally reveal the secrets behind these features, shedding light on the forces that shaped Venus and its place in the solar system. Now turning to another fascinating feature of Venus, we encounter the mysterious crustal plateaus, vast highland regions that stand out dramatically against the planet's otherwise relatively flat surface. These plateaus, some of the most prominent geological features on Venus, rise high above the surrounding plains, creating a stark contrast that has puzzled scientists for decades. Unlike the ridges and troughs we explored earlier, these plateaus are massive, elevated regions that seem to defy the typical geological processes we see on other planets. One of the leading theories about the formation of these crustal plateaus involves mantle plumes, massive upwellings of hot material from deep within Venus's interior. On Earth, mantle plumes are responsible for creating volcanic hotspots like the Hawaiian Islands. On Venus, however, these plumes may have pushed the planet's crust upward, forming these expansive highlands. The process is thought to have involved the crust thickening and rising as the mantle material pushed against it, creating the elevated plateaus we observe today. This theory suggests that Venus's interior was once far more active than it is now, with powerful forces reshaping its surface over billions of years. Another intriguing possibility is that ancient tectonic activity played a role in the formation of these plateaus. While Venus lacks the plate tectonics we see on Earth, some scientists believe that the planet may have experienced a different form of crustal movement in the past. This activity could have caused sections of the crust to buckle and rise, forming the plateaus. The idea is supported by the complex patterns of fractures and ridges found within these highland regions, which hint at significant stress and deformation in the planet's crust. This theory challenges our understanding of how planetary surfaces evolve, suggesting that Venus's geological history may have been far more dynamic than we once thought. What makes these crustal plateaus particularly fascinating is their unique composition and structure. Unlike the volcanic plains that dominate much of Venus's surface, the plateaus are thought to be made up of older, more rigid crustal material. This difference in composition could explain why these regions have remained elevated while other areas have been reshaped by volcanic activity. Additionally, the plateaus often feature steep cliffs and deep valleys, suggesting that they have undergone significant erosion or collapse over time. These features provide valuable clues about the forces that have shaped Venus's surface and the planet's internal heat distribution. The study of these crustal plateaus also offers insights into Venus's overall geological history. By analyzing their size, shape, and distribution, scientists can infer details about the planet's interior and the processes that have driven its evolution. For example, the presence of large, elevated plateaus might indicate areas where the crust is thicker or where mantle plumes have been particularly active. Similarly, the fractures and ridges within these regions could point to periods of intense tectonic stress. These clues help researchers piece together the story of Venus's past, shedding light on how it became the planet we see today. As we continue to explore Venus, these enigmatic crustal plateaus serve as a reminder of the planet's complex and dynamic history. They challenge our assumptions about planetary geology and highlight the need for further investigation. Future missions, equipped with advanced imaging and radar technology, may finally reveal the secrets behind these highland regions, offering new insights into the forces that shaped Venus and its place in the solar system. Now shifting our focus to the vast lowland plains of Venus, we encounter a stark contrast to the towering crustal plateaus we just explored. These expansive lowlands, covering much of the planet's surface, present a mystery that has intrigued scientists for decades. Unlike the rugged highlands, the lowlands are relatively flat and smooth with few prominent features. This uniformity raises questions about how these plains formed and what they reveal about Venus's geological history. One of the leading theories suggests that the lowlands were shaped by massive volcanic flooding. On Venus, volcanic activity has played a significant role in reshaping the surface, and it's possible that vast amounts of lava once flowed across these regions, filling in depressions and creating the smooth plains we see today. This process, known as volcanic resurfacing, could explain why the lowlands lack the complex terrain found in other areas. The lava would have cooled and solidified, forming a flat, featureless landscape that contrasts sharply with the planet's more rugged regions. Another intriguing possibility is that tectonic subsidence contributed to the formation of the lowlands. Subsidence occurs when the planet's crust sinks due to the weight of overlying material or the movement of tectonic forces. On Venus, this process could have caused large sections of the crust to drop, creating broad, low-lying basins. Over time, these basins may have been filled with volcanic material, further smoothing the surface. This theory aligns with the idea that Venus's crust is more rigid and less dynamic than Earth's, allowing for large-scale subsidence without the fracturing seen in plate tectonics. What makes the lowlands particularly fascinating is their role in understanding Venus's geological evolution. The smoothness of these plains suggests that they are relatively young compared to the planet's highlands, which bear the scars of ancient tectonic and volcanic activity. This age difference provides valuable clues about the timing and intensity of geological processes on Venus. For example, if the lowlands were formed by volcanic flooding, it would indicate that Venus experienced significant volcanic activity in its recent geological past. Similarly, evidence of subsidence could shed light on the planet's internal dynamics and how its crust responds to stress. The lowlands also offer insights into Venus's surface conditions. Their flat, unbroken terrain suggests that they have been less affected by erosion or other surface-altering processes. This could be due to the planet's thick atmosphere, which shields the surface from the kind of weathering seen on Earth. Alternatively, it might indicate that the lowlands have been resurfaced more recently, erasing any older features. Either way, these plains provide a unique window into the forces that have shaped Venus over billions of years. As we continue to study Venus, the lowlands remain a key area of interest for scientists. Their formation and evolution hold important clues about the planet's interior, its volcanic history, and its overall geological activity. Future missions equipped with advanced radar and imaging technology may finally unravel the mysteries of these vast plains, offering new insights into Venus's past and its place in the solar system. For now, the lowlands stand as a testament to the planet's complex and dynamic nature, challenging our understanding of planetary geology and inspiring further exploration. Now shifting our gaze to the skies of Venus, we encounter one of the planet's most puzzling phenomena: the strange atmospheric waves that ripple through its upper atmosphere. These waves, detected by various spacecraft and telescopes, are unlike anything observed on Earth or other planets in our solar system. Their unpredictable behavior and mysterious origins have left scientists scratching their heads, offering yet another layer of intrigue to Venus's already enigmatic atmosphere. Atmospheric waves on Venus are thought to form due to the planet's extreme atmospheric conditions. With surface temperatures hot enough to melt lead and an atmosphere composed mostly of carbon dioxide, Venus's environment is a pressure cooker of sorts. The thick atmosphere, which is about 90 times denser than Earth's, creates a unique setting where waves can propagate in ways that defy conventional atmospheric science. These waves are believed to be driven by the planet's superrotation, where the atmosphere whips around the planet much faster than the surface rotates. This rapid movement generates powerful winds and turbulence, which in turn create the conditions for these atmospheric waves to emerge. What makes these waves particularly baffling is their erratic behavior. Unlike Earth's atmospheric waves, which tend to follow predictable patterns, Venus's waves appear to form and dissipate without clear rhyme or reason. Some theories suggest that the waves are influenced by the planet's topography, with mountains and other surface features disrupting the flow of the atmosphere and creating ripples that travel upward. Others propose that the waves are linked to thermal tides, where the intense heating of the atmosphere by the sun causes it to expand and contract, generating wave-like motions. However, neither theory fully explains why these waves are so transient and unpredictable. Another intriguing aspect of these atmospheric waves is their connection to Venus's superrotation. The planet's atmosphere rotates around it in just 4 Earth days, while the surface takes 243 days to complete a single rotation. This stark difference creates a dynamic and chaotic environment, where the interplay between the atmosphere and the surface could be driving the formation of these waves. Some scientists believe that the waves act as a kind of atmospheric brake, transferring momentum between the upper and lower layers of the atmosphere and helping to maintain the superrotation. If true, this would provide valuable insights into the mechanisms that sustain Venus's bizarre atmospheric behavior. The study of these atmospheric waves is not just an academic exercise, it has practical implications for understanding Venus's climate and weather patterns. By unraveling the mysteries of these waves, scientists hope to gain a better understanding of how energy and momentum are distributed within the planet's atmosphere. This, in turn, could shed light on broader questions about atmospheric dynamics on other planets, including Earth. For example, studying Venus's waves might help us understand how extreme atmospheric conditions, such as those caused by climate change, could affect weather patterns on our own planet. As we continue to explore Venus, these atmospheric waves remain a key area of interest for researchers. Future missions, equipped with advanced instruments capable of probing the planet's upper atmosphere in greater detail, may finally uncover the secrets behind these elusive phenomena. Until then, the waves stand as a testament to the complexity and unpredictability of Venus's atmosphere, challenging our understanding of planetary science and inspiring further exploration. With each new discovery, we move closer to unraveling the mysteries of this enigmatic world and its place in the solar system. Now turning to one of the most tantalizing mysteries of Venus, we delve into the controversial theory that microbial life could exist within the planet's clouds. This idea, once considered far-fetched, gained significant attention with the discovery of phosphine gas in Venus's atmosphere. Phosphine, a molecule often associated with biological processes on Earth, was detected in the planet's upper cloud layers, sparking a heated debate about the possibility of life thriving in such an extreme environment. The presence of phosphine on Venus is puzzling because on Earth, this gas is primarily produced by living organisms or industrial processes, while non-biological sources of phosphine, such as volcanic activity or chemical reactions, cannot be entirely ruled out. None of these explanations fully account for the levels detected. This has led some scientists to speculate that microbial life, adapted to survive in the acidic clouds of Venus, could be producing the gas. If true, this would revolutionize our understanding of life's potential to exist beyond Earth. However, the idea of life in Venus's clouds is not without its challenges. The planet's atmosphere is incredibly hostile, with clouds composed mostly of sulfuric acid and temperatures that fluctuate dramatically. While the upper cloud layers are relatively cooler, they are still far from hospitable by Earth standards. Any potential microbes would need to possess extraordinary adaptations to survive in such conditions, including resistance to extreme acidity and the ability to harness energy from chemical reactions rather than sunlight. Studying Venus's atmosphere to confirm or refute the presence of life is no easy task. The planet's thick clouds and corrosive environment make it difficult for spacecraft to collect reliable data. Current missions such as NASA's upcoming Defy Plus and Veritas aim to probe Venus's atmosphere and surface in unprecedented detail. These missions could provide crucial insights into the origins of phosphine and the potential for life in the clouds. Until then, the debate remains open, with scientists on both sides presenting compelling arguments. The implications of finding life on Venus would be profound. It would not only challenge our assumptions about where life can exist, but also raise questions about the origins of life in the solar system. Could life have emerged independently on Venus, or is it possible that microbial life was transported between planets by meteorites? These questions highlight the importance of continued exploration and the need for innovative approaches to studying Venus's atmosphere. As we ponder the possibility of life in the clouds of Venus, we are reminded of the planet's enduring mysteries and the questions that still await answers. Whether or not microbial life exists on Venus, the discovery of phosphine has reignited interest in this enigmatic world and underscored the need for further exploration. With each new mission and discovery, we move closer to unraveling the secrets of Venus and understanding its place in the cosmos. As we bring our journey through the 25 unexplained mysteries of Venus to a close, it's clear that this enigmatic planet continues to defy our understanding. From its runaway greenhouse effect and missing water to the bizarre super-rotation of its atmosphere and the tantalizing possibility of life in its clouds, Venus presents a puzzle that challenges not only our knowledge of the planet itself, but also our broader understanding of the solar system. Each mystery we've explored reveals just how much we still have to learn about this fiery world and its place in the cosmos. The importance of future missions to Venus cannot be overstated. Upcoming endeavors like NASA Veritas and Defy missions promise to shed new light on these enduring questions. By mapping the planet's surface in unprecedented detail and probing its atmosphere for clues, these missions could unlock secrets that have eluded us for decades. They represent the next chapter in humanity's quest to understand Venus and, by extension, the forces that shape planets like our own. As we look to the future, we invite you to reflect on the mysteries we've uncovered. Which one intrigues you the most? Is it the possibility of microbial life in the clouds, the strange lightning that defies explanation, or the enigmatic dark streaks that hint at unknown processes? Share your thoughts in the comments below. We'd love to hear your perspective. And don't forget to like, subscribe, and hit the notification bell so you never miss an update as we continue to explore the wonders of space. The mysteries of Venus are just the beginning, and there's so much more to discover. Stay curious, and let's keep unraveling the secrets of the universe together.